You know, humanity pumps out over 2.5 quintillion bytes of data every single day. The volume is just unfathomable. So how on earth do we make sense of it all? Well, welcome to this explainer. Today we're going to demystify how computers manage to extract the absolute most important parts of massive datasets and do it without getting completely lost in dense mathematical proofs. We're looking at a truly fascinating paper from researchers at the University of Mons that literally changes the game on how we compress and understand complex data. Let's get right into it.
I mean, we've all wondered this at some point, right? How exactly do algorithms take messy, chaotic, real-world data, like thousands of face images, hours of audio, or piles of text documents, and compress it into something actually interpretable and useful? How does a machine look at a giant sea of numbers and figure out what actually matters? And crucially, how does it do this without resorting to some uninterpretable black box model where even the programmers have no idea how it got the answer? Well, that, my friends, is the magic of dimensionality reduction, and it's the core of what we're unpacking today.
So here's our roadmap for this explainer. First, the dimensionality reduction dilemma. Second, the strict separability assumption. Number 3, introducing generalized separability. 4, 2 ways to solve it. 5, putting it to the test. And finally, number 6, extracting features.
All right, let's start with section 1, the dimensionality reduction dilemma. This is a fundamental problem.
A major tool data scientists use here is called non-negative matrix factorization, or NMF for short. It's an absolutely amazing mathematical trick for compressing data. Think pixel intensities in an image or text counts in an article into basic, interpretable parts. Imagine you take a massive, overwhelming spreadsheet of data and basically boil it down into 2 smaller, much easier to read spreadsheets. And the magic is, when you multiply those 2 smaller spreadsheets together, they recreate the original data perfectly. Now, because the data is non-negative, meaning 0 negative numbers allowed, the resulting parts are highly interpretable. Practically, this is super important. If you're tracking how many times the word economy appears in a news article, you can't exactly have a count of -5, right? You can't have negative pixels either. Keeping it strictly positive keeps the whole thing grounded in reality.
But, okay, there is a massive catch. Standard NMF is incredibly hard to solve computationally. It's what computer scientists call NP-hard, which is basically just a polite academic way of saying that if you tried to brute force a solution, the universe would probably end before your laptop finished doing the math. To make matters even worse, there often isn't just one unique answer. You could run the algorithm and end up with multiple different interpretations of the exact same data. And honestly, that's not very helpful at all when you're looking for that single, true underlying pattern.
To fix this, we move to section 2, the strict separability assumption. It's a clever workaround.
So researchers previously introduced this workaround and called it separable NMF. This approach essentially assumes that the basic building blocks of your data actually exist as individual, pure data points right there inside the dataset itself. Think of it kind of like a painting. If you want to understand the colors in that painting, separable NMF assumes that somewhere on that canvas there's a pixel of pure unmixed red, a pixel of pure blue, and one of pure yellow. By just making this one assumption, a math problem that was virtually impossible suddenly becomes solvable in polynomial time. That just means a computer can actually finish the job while you're still alive to see the results. And it's been a real game changer for things like hyperspectral unmixing and audio separation.
But wait, there is a catch here too. The separability requires that for each topic there has to be at least one completely pure document discussing only that topic. So, if we apply this to document classification, it requires completely pure data points for every single topic. It assumes there's a document out there discussing solely sports and absolutely nothing else, or only politics and nothing else. Let's be real, in our messy reality, that is exceedingly rare. Real articles mix topics all the time.
Enter the heroes of our explainer. Section 3, introducing generalized separability. This is a new, flexible approach.
Take a look at this comparison. On the left, we've got the old, strict rule. You absolutely must have a pure document for every single topic. But on the right, generalized separability totally relaxes those rules. It says a topic just needs either a pure document or simply a unique anchor word. An anchor word is just a word that only ever appears when a specific topic is being discussed. By asking for just an anchor word instead of an entire pure document, the algorithm suddenly makes vastly more sense for real-world datasets. It's a huge shift.
By opening up this kind of flexibility, the algorithm falls into this perfect Goldilocks zone. The authors of the paper call it GSNMF. It compresses data far more efficiently while still remaining computationally solvable. It requires significantly fewer rank 1 factors, which, by the way, are essentially just the core mathematical building blocks of the algorithm, to reconstruct the input matrix, especially when you compare it to those older strictly separable models. It's basically doing more with a lot less.
So how do they actually execute this new math? That brings us to Section 4, 2 ways to solve it. Algorithms in action.
The paper lays out 2 distinct algorithms to actually make this generalized separability work. The first one is called GSFGM. This is a highly accurate convex optimization model that uses a fast gradient method. Now, convex optimization essentially just means the math is structured so that it's guaranteed to slide all the way down to the absolute best possible answer without getting stuck on some mathematical false peak along the way. It's incredibly precise, but yeah, it's a bit computationally heavy. The second one is this super fast heuristic approach called GSPA, or Generalized Successive Projection Algorithm. It's specifically designed to be quick and to scale linearly right alongside the size of your data.
This heuristic GSPA is actually really cool because it sequentially extracts the most important data points through 3 pretty straightforward steps. At each iteration, first it finds the column or row with the largest mathematical weight or norm, which acts as our anchor. Then it projects the data away. Think of this like mathematically filtering out the anchor we just found so we can clearly see what the next most important feature is without that first one blocking our view. Finally, it just repeats the process to find the next most important piece of data. Simple, but highly effective.
All right, let's look at the actual data. Section 5, putting it to the test, real-world data results. Get this, in experiments on fully randomly generated data, the GSFJM model hit exactly 100% accuracy in identifying the correct row and column indices at low noise levels. 100%. It flawlessly extracted the ground truth factors that the researchers used to generate the data in the first place. This is basically the ultimate sanity check, proving the math is absolutely rock solid in a controlled environment before anyone tries to release it out into the wild.
If you look at this graph, notice that blue line right at the very top. That represents GSFGM. It stays perfectly flat, heavily outperforming the older, strict separability models, which you can see way down below in green and yellow. And what's impressive is that even as noise is actively introduced to the dataset, GSFGM remains just incredibly robust and accurate.
Now, the really crucial point here is that the researchers didn't just test this on easy, random noise. They purposely injected tricky adversarial middle point noise. This was designed specifically to throw the algorithms off balance by pushing data points outside their expected boundaries, or what mathematicians like to call the convex hull. But even under these harsh adversarial conditions, GSFGM still reliably identified the true underlying factors. It completely left standard models in the dust, as those older models basically fell apart and got stuck in bad local minima.
Okay, so how about real text? When applied to real news articles from the TDT-30 dataset, the algorithm successfully matched pure documents with highly specific anchor words to categorize the text with amazing accuracy. The algorithm neutrally analyzed the text and pulled out pure documents discussing major global events, while simultaneously identifying very specific anchor words like Pakistan, Iraq, and Lewinsky that strictly define their respective topics. It proves this hybrid approach works perfectly on the complex, messy reality of real-world journalism.
Now we transition into an entirely different application. Section 6, Extracting Features, Faces and Pixels.
This is where we jump from abstract text datasets to something highly visual. When it's fed massive datasets of facial imagery, the math translates into finding the most essential pixels and the most representative subjects needed to rebuild the whole database. So instead of just mathematically blurring the images to save a bit of space, the algorithm is actually finding the true foundation stones of the dataset. Just look at how brilliantly the algorithm plucks out extreme lighting conditions and unique facial angles from the Frey and Yale datasets to serve as its core foundation. It identifies a few key pixels, often right around the edges or unique contours of the face. And why does it do that? Well, because if an algorithm can mathematically understand the extreme shadow on the left side of a face, it essentially learns the geometry of a human nose and cheekbone. From just those few extracted pieces and distinct expressions, it can successfully reconstruct an entire database of thousands of faces. It's honestly mind-blowing.
All of this leaves us with a pretty massive question. If this flexible algorithm can perfectly decode the foundational geometry of faces and pinpoint the distinct anchor words of massive text databases, what other gigantic, chaotic datasets is it about to conquer next? Just think about the possibilities in fields like medical imaging, climate data analysis, or even tracking financial markets. We are moving into an era where machines don't just compress our data, they extract its true interpretable essence. Thank you so much for joining me for this explainer, and keep questioning the data around you.